So I have this mouthful of a talk title which I can barely pronounce myself in my jet-lagged state. But suffice it to say that this is the first talk in the formation channels session. And so I thought I would start with a quick overview of why we even bother talking about formation channels, right? Because forming merging binary black holes is easy, right? You take two stars. Here are two happy stars. They are orbiting around each other. As they orbit around each other, they eventually collapse into black holes, or maybe neutron stars. They continue orbiting around each other. Then we wait for a while. Gravitational waves are emitted. We wait for a while longer. The two objects come together. Dave Wrightsey very proudly waves his grandfather's gold watch. Kip Thorne shows off his Nobel Prize. Everybody lives happily ever after, right? That's it. So it's easy, right? So why are we having this session? Well, the reason we're having this session is because there's what I would call the fundamental theorem of gravitational wave astrophysics, which is it's really hard to force compact objects to merge in the age of the universe. You need to find some tricks in order to persuade them to come together. And the reason you need to find those tricks is fundamentally a story of two parts. Part one is gravitational waves, while being, of course, very efficient at radiating energy. We've all heard that during the merger of two black holes, the gravitational wave luminosity outshines all the stars in the visible universe by several orders of magnitude. This is true when the two objects are very close. And of course, it's not true when the objects are far apart. Gravitational wave energy or efficiency, or energy radiation efficiency scales very strongly with the separation. And it means you can ask the following question. How far apart can two compact objects be to be able to merge just through the emission of gravitational waves within the age of the universe? And so that's what this plot shows. You can ignore the higher eccentricity lines. Let's just focus on the blue line, which is the zero eccentricity line. And this shows the periapsis in solar radii as a function of the component mass, assuming you have equal masses. And what this tells you is if you have, for example, two black holes that are 30 solar masses each, they can only be about 50 solar radii, or about a quarter of an astronomical unit apart, if you want that binary to merge within the age of the universe through the emission of gravitational waves. OK? Fine. So it means we cannot take any two stars. We just have to take two stars that are no further than this apart, no more than about a quarter of an AU. Right? That's fine. Well, here comes the other problem. When stars get old, they don't go to the gym very much, and they kind of bulk up a little bit. Fortunately for us humans, we don't do it nearly as badly as stars do. I mean, we might get a love handle here or there, but stars do it by about 3 orders of magnitude, right? Vicky is commenting on my appearance. So stars, you have a star that starts out, let's say, at zero age in the main sequence, at, even for a fairly massive star, at maybe order of 10 solar radii, and at later stages of its evolution, it becomes a giant that's maybe 1,000 solar radii, or thousands of solar radii, depending on other factors like metallicity, several astronomical units. So we basically have a problem. We're trying to fit not so much a square peg into a round hole as a peg that's this big into a hole that's this small, if we want those two stars to survive during their evolution, right? Because if they get bigger than the size of the binary, nominally you expect that they would just end up merging and you're done as stars, not as black holes. How do you fit them into this binary and then allow them to merge within the age of the universe? And so, of course, people have suggested several solutions to this. So here's a little sketch courtesy of an artist from nature who was very good at rendering something I drew with my son's crayons into something that almost looks nice. And the two channels on the right I won't talk about. So the one on the far right is where stars actually form black holes or compact objects independently of each other. And then they sign up to a dating website, and they're introduced to each other after the fact. Okay, in this case, they introduce each other by other stars going around them. So this is dynamical mergers in a dense stellar environment, and Fred and Smadar will talk about this tomorrow. In the middle here is a very special situation where you have chemically homogeneous evolution, efficient mixing, and the stars therefore don't expand magically. There's a little magic wand that says abracadabra, and Selma will tell you in a moment exactly how that wand is being waved over here and why in some cases stars don't expand, and so you can really have these two stars start close together, avoid expansion, and then form two black holes that merge in Hubble time. I will tell you about the channel on the left, which is one where you kind of magically start with the stars being much further apart than they could be and still merge in the age of the universe, but sufficiently close that they will interact with each other during their evolution as they expand, and then you bring them closer together just at the right moment, and that magic wand that brings them closer together, that's this common envelope phase. So, of course, there have been probably hundreds of papers by now about the common envelope phase. I'm not going to go through all of them, and if you can read, here's sort of a small list of them. Of course, there are many, many more that didn't make it onto this list. This is a plot from a paper by Chris Belczynski and company, including Dan Holtz, who's in the audience here, that describes how you might have formed the first LIGO detection GW150914. But given that it's so late in the day, and many of you, like me, are probably also jet-lagged, let me try to do a simpler version of this. Oh, maybe. Let's try this again. Very good. OK. So you grow up on the planet Tatooine. You see two stars in the sky above you. George Lucas was a visionary, or a very good astronomer, because he knew that actually binaries are much more common than single stars. Stars don't like being alone. And there was two stars. Let's call them Stella and Estelle. They're good friends. They're in an orbit. They're orbiting around each other. They're not just normal stars. They are pretty cool stars. In fact, they're rock stars. They're rock stars because they burn bright and sadly die young. So in this case, they're very massive stars. They are, in the case that we want to make neutron stars, roughly more than 8 solar masses. If we want to make black holes, roughly more than 20 solar masses each. And so they are rock stars. There is all kinds of potpourri. Oh, well, I don't know what's going on. OK. And at some point, these rock stars, this is really, OK, hold on. Yeah, OK. Now let's try that one more time. OK, there's all kinds of potpourri flying out because these rock stars are, of course, losing mass at a very high rate through winds. And at some point, one of them, even rock stars, do eventually bulk up a little bit. And so one of them, let's say in this case Stella, she was the more massive star to begin with. So she evolves a little bit faster, and she starts expanding. And as she expands, she overflows her Roche lobe, meaning that she is starting to be tidally pulled apart by the companion star. And there's some mass transfer going on. Maybe the binaries properties change a little bit because of the mass loss. If the mass transfer is not completely conservative, some of the mass just goes off into space. And maybe it looks something like this. So here you have a little possible picture of what a mass transferring system might look like. And you might have a situation where the mass transfer really gets down and dirty, where you have a dynamically unstable mass transfer. So the more mass is transferred from one star to the other, the faster the mass transfer rate wants to become, the more the star fails to fit inside its Roche lobe. So we're going to close this off with a common envelope so that we don't see too much into the details of the lives of these stars. And that phase is the thing that allows the binary to really come closer together right at the time when you need it to, because this is when you remove the stellar envelope and bring the star down to its core, which is much more compact. So you bring the stars closer together, you eject the envelope, take the energy out of the envelope, therefore hardening the binary, bringing closer together, and allowing yourself the opportunity to merge the two complex objects as gravitational waves. OK, so now, oh, and of course at some point the stars go supernova, form your neutron stars and black holes. And now if you put this whole picture together, OK, here's a variation on the plot I showed you earlier from Belczynski et al. This is from my student's paper, Simon Stevenson. And this is, for example, how you might have formed the progenitor to one of the other sources, GW 151226, through this channel. So let me just quickly walk you through this. OK, start out with two main sequence stars, fairly massive, in this case about 60 and 30 solar masses, separated by several astronomical units, far too distant to merge in the age of the universe, so they just collapse into black holes. Then the primary star expands, takes several million years, of course, before it ends its main sequence evolution. The helium core contracts, the hydrogen envelope expands, and it starts to transfer mass onto the companion. When it does this, most of the mass, in fact, is ejected into space. Some of the mass ends up accreting onto the companion. The binary can even potentially harden during this mass transfer, depending on the setup and the exact mass ratio. Here it slightly shrinks. For slightly different mass ratios, it can actually widen even further. Ultimately, this star, which is now a Wolf-Rayet star, just a helium star, collapses into a black hole. Another couple of million years later, the secondary now begins to expand. As the secondary expands, the secondary overflows the Schroth lobe. Now this is essentially completely non-conservative mass transfer because the primary is a black hole, so it's limited to accreting at the Eddington rate under our assumptions. And so in this particular mass transfer episode, when you're transferring mass from an evolved giant star that's already helium burning in the core but with a hydrogen envelope around onto a black hole, we argue that this should be a common envelope phase, so this dynamically unstable mass transfer. Now, of course, there are lots of people who have been working on the detailed simulations of common envelope evolution. I'm not going to discuss that right now. We can talk about that separately. But in this case, we're using simplified prescriptions for this. And the argument is that you basically have now a black hole and the core of the companion orbiting around each other inside this rather dense envelope of hydrogen gas. As they're doing it, there's dynamical tidal friction against the envelope. There's drag from the envelope. And this is heating up the envelope, removing the orbital energy from the binary. Ultimately, the envelope can be expelled. And if it's expelled, you're left with two objects that are much closer together by where you've lost an amount of energy from the orbit that's roughly comparable to the binding energy of the envelope. And that means that you can harden the orbit by something like 2 orders of magnitude. So here you go from about 700 solar radii to just a few solar radii. And now you have a Wolf-Rayet star in orbit around a black hole. So this would look like a high-mass X-ray binary to an observer who happens to catch it during this phase. Ultimately, the Wolf-Rayet star collapses into a black hole. And now you just sit there and wait patiently for a few billion years for gravitational waves to do their dirty work, and this binary merges and forms a LIGO source. So this could at least be one of the ways in which you end up forming these LIGO sources. So now let's ask a few questions. So one of the questions you can ask is, OK, so I told you about one possible channel, this common envelope evolution channel. There are a few bells and whistles you can add on to this. So for example, sometimes you can have a situation where you can have a double common envelope where in fact, both stars are fairly evolved when they first engage in mass transfer, and you simultaneously remove the envelopes of both stars during envelope ejection. You can have another situation where maybe you have stable mass transfer, but stable mass transfer from a rather massive star onto a compact object that leads to significant hardening of the binary. So this is something that Selma at Wadenhovel and Simon Partridge-Swart worked on recently, for example, and that in some cases you can get binary black hole mergers through that variant actually foregoing a common envelope altogether. But roughly speaking, this kind of channel with expanding stars and mass transfer could conceivably be responsible for all of the binaries that LIGO has seen, at least if you look at the masses. So here's an argument that says, OK, this is a population synthesis study where we start with millions of binaries, we evolve them forward, and we pick out those which happen to, at the end, merge while matching the masses of the observed LIGO sources. Okay, this was done for the first 4 sources in this paper. That's all that we knew of at the time this paper was published. And you can see, of course, that the progenitors occupy different regions in the initial mass space. And for forming the most massive black holes, you really have to go to lower metallicity, something like a 20th of solar metallicity in this case, because going to lower metallicity allows you to reduce stellar winds and therefore preserve more of the mass, end up with more massive black holes. But basically, okay, it looks like you can do this. And in fact, you can continue doing this with all of the LIGO events seen so far. This is from a paper led by another PhD student, Alejandra Viña Gomez, that's hopefully coming out later this week. Okay, so population synthesis says, yes, in principle, you can form all of your black holes and neutron stars so far through this channel, but that's not very convincing. The reason it's not very convincing is there are lots of questions, and all that we've done so far is tried a few prescriptions, a few recipes for how to resolve these. What's the initial separation distribution between the stars, and what's their initial mass distribution? How much mass is actually lost during mass transfer? How conservative is it? And what is the specific angular momentum carried away by the mass that is lost? How much of a kick do black holes get during a supernova? And how much mass do they lose during a collapse? Or is there no supernova at all? If the black hole progenitors are heavy enough, do you just have a complete collapse with complete fallback? The common envelope phase is, well, it's all question marks. How strong are the winds during the Wolf-Rayet phase, during the luminous blue variable phase, and so on and so on. In fact, the only thing that I don't have question marks on are the gravitational waves, because those actually seem to work pretty well. So even Fred agrees with that. So how do we deal with this, with the fact that there are lots of question marks? Well, one possibility is, population synthesis, one of its benefits is that you can parameterize a lot of your uncertainties in a fairly straightforward way, right? You can describe all of your unknowns as some free parameters in the model that describe the evolution. Think of them as coefficients in differential equations that you aren't sure about, and you solve in a Monte Carlo simulation the same set of initial value problems, but with slightly different prescriptions, slightly different differential equations, and you get different outcomes. And people have, of course, done this, but they've done this with a couple of different models in the parameter space. So you can measure the parameters here. Okay, here we've plotted for another student, Jim Barrett's paper, 3 of these parameters describing the luminous blue variable winds, the typical kick velocity for black holes, and the common envelope efficiency parameterized in a particular way. And you can populate the space, but as you can see, you cannot afford to populate it very densely. Models are still somewhat expensive. So one of the things we've tried to do, and this is something that I think is relatively new in this field. People, of course, have been making models like this for a while. We've tried to actually build emulators in the space so that you build a few models, and then you figure out what the prediction would have been even in a place where you have not run a model, so that we know what is the expected merger rate of black holes and the expected distribution of black hole masses, even in places where we don't have any models. And so this is what this might look like. Will this? It's supposed to be an animation. I don't know if it'll work. No, it doesn't work. OK. All right. So apparently animations don't work with this thing. Let me see if it works, if I should just click on it by hand. OK. So it's moving. OK. So it's showing you basically what all this is trying to show you is that in green are our actual validation simulations. In blue are our predictions. And you can see that the predictions are actually quite good. We correctly predict what the mass distribution of merging black holes would be, even in regions of the parameter space where we have not specifically used that model for building our emulator. OK, what else can we do? Well, we can look at the predictions then, since we have this ability. So we can, for example, say, OK, what is the expected distribution of the masses? OK, in this case, the chirp mass of the emerging binary black holes. OK, there are 3 plots here. In orange, the local distribution at a redshift of 0. In green, redshift of 0.5. In blue, the redshift of 1. You can see, by the way, that OK, in this particular model, which we called our fiducial model, the local merger rate that we had was about 80 per cubic gigaparsec per year, which is consistent with the LIGO rate so far. And of course, it would be higher at higher redshifts. Now, because there's both a larger star formation rate and, more importantly, a larger fraction of it happening at low metallicity. But more interestingly, you can start playing the kinds of games that Neil told you about in the previous session, but now applying them not to individual systems, but to entire populations, right? So Neil told you how to estimate parameters of individual binaries. If you have an individual binary, you can use this procedure of Bayesian inference to say what were the masses, what were the spins, and so on. Okay, I'm no longer interested in individual binaries. I was for a number of years. Now, other people are continuing to work on the problem, and I'm trying to understand what can we learn about population parameters, the astrophysical parameters that govern binary evolution. And the answer, it turns out, is that you actually can constrain them quite well if you have sufficient numbers of observations. So here, for example, if we consider a multidimensional parameter space describing various uncertainties in common envelope physics, kick velocities, and so on and so forth, and concluded that after 1,000 observations, something you can realistically get to after a couple of years of design sensitivity observations for advanced LIGO, you can measure these, constrain these parameters to an accuracy of only a couple of %. Now, one caveat I should add here is that one of the things we did not include in there is the uncertainty in the star formation rate, and particularly metallicity-specific star formation rate. So what these curves show is the overall density of mergers and density of detectable mergers as a function of redshift. And the difference between the curves is basically different prescriptions for the metallicity distribution of star formation as a function of redshift. And you can see that there are huge variations, in fact, in some cases up to an order of magnitude, just from the uncertainty in the metallicity distribution of star formation. Okay, what else can we learn about from detections? Well, one thing we can do, so here is actually trying to learn not from detections of binary black holes or LIGO observations, but detections of binary neutron stars in the galaxy, which we know of as radio pulsars in binaries. We can use those to constrain binary evolution. So here, we applied the same population synthesis models, evolution through a common envelope phase, which really does seem to be consistent with forming galactic neutron star binaries, to the binary population. And we found something very strange. You can ignore the color of the dots. This shows the period eccentricity distribution. In yellow and orange, you can even ignore the blue ones, are the binaries we predict should form according to our models. And the purple diamonds are the ones that have actually been observed. Right, so here is, somewhere over here is the Hals-Taylor binary, somewhere over here is the double pulsar JO737. And you see, this is a terrible match. So something is very wrong there. Well, we figured out what was wrong. We didn't correctly account for what would happen during so-called KSBB mass transfer when the progenitor of the neutron star, when progenitor of the secondary overflows its Roche lobe, potentially for a second time at the end of the helium main sequence after it's already gone through a common envelope phase. And once we account for that behavior correctly, namely, in this case, correctly seems to be that you don't go through a second common envelope phase, you have stable mass transfer, you end up with a prediction that matches the observed distribution much better. So we really can place constraints on binary evolution by doing this. Another example, okay, since Will is not here, he probably would have shown this plot, but this was a paper that Will led that we worked on together last year. And this is trying to look now not at the masses, but at the spins. So these are the spins of the first 4 LIGO detections, specifically the spin component, the average spin component in the direction along the orbital angular momentum. And the question we wanted to ask was, are these consistent with either isolated binary evolution, like the kind that I described now, where you might expect that on average the spins are going to be aligned with each other or preferentially aligned, or dynamical formation of the kind that Fred and Smadar will tell you about tomorrow, where because there's a lot of randomness in the assembly, you don't necessarily expect any preferential alignment between the spins. You might expect the spin distribution to be isotropic. And what we concluded here was that we really can tell already with overwhelming probability that, for example, high spin magnitudes and preferentially aligned spins with the orbital angular momentum are very strongly disfavored. So instead, it must be the case that either spins are low in magnitude or spins are preferentially misaligned, possibly pointing to a significant contribution from the dynamical formation scenario. Now, personally, I actually tend to think that the answer is that spins in black holes are just low in magnitude. But we can discuss it separately. OK, so I realize I'm out of time, so I'm going to skip these last two slides about hierarchical modeling. But the only point I wanted to make on the hierarchical modeling slides was just to say that, of course, we don't know what the right formation channel is, but we don't have to argue about what it is. We're getting better and better data. And so the correct answer is to allow for the fact that there might be multiple channels that are all playing a role. And we can actually have a framework which allows us to say that there's an admixture model from multiple channels and simultaneously try to model the distributions and the properties of systems coming from these multiple channels. And ultimately, we want to bring together the observations, the models, and statistics in order to do something like a concordance model of binary evolution, where we use different observations, gravitational wave and electromagnetic ones, to constrain all of these uncertainties in stellar and binary evolution and really learn from the gravitational wave population, discover how massive stars and binaries evolve. Thank you.
So I know that people always say the common envelope part is complete magic and we don't have observational constraints, but is there numerical simulation work being done to actually constrain the range of possible outcomes, or is that just way too complicated?
There is a lot of numerical simulation work. There are lots of issues with numerical simulations, but you can look, for example, at let's say papers being written by people like Natasha Ivanova, that Natasha has been spending the last 15 years trying to do precisely that, and a number of other people as well. I think one can also make some progress thinking about this in an almost phenomenological way as well. So, for example, one of the questions I think is not just the overall energy budget, but one of the issues we should really be focusing on is the time scale. So one of the questions is, OK, fine, you deposit energy in the envelope. You might deposit enough energy to eject the envelope, but if the rate at which you're proceeding with your in-spiral, which can be quite high, is faster than the rate at which thermally the energy can be distributed throughout the envelope, you just leave behind hot spots buried within the envelope. So you can have plenty of energy there, but you won't eject the envelope at that point. So these are the kinds of calculations you can do back of the envelope, and I think they can give you a pretty good handle actually on what's going on. But absolutely, the answer is yes. First of all, there are people trying to do this modeling, and secondly, there might be some observational constraints as well. So I think, in fact, Morgan McLeod has a poster out there about luminous red nova, and which might very well be signatures of common envelope ejections. That's something we're working on as well, trying to use those as additional observational constraints.
So I must be missing something, because the events that were reported by LIGO, maybe you can explain that, they're very high signal to noise, okay? And statistics tells you that there must be many more that are lower signal to noise. Now, if you're trying to interpret the population that was observed or reported so far, you might be missing the features of the bulk of the population that has not been reported so far, which is much more numerous, and that accounts for most of the events. So am I missing something?
No, you're absolutely right. So what we try to do is we try to ask the question, so it's very difficult. OK, this is more of a statistics question, but it's in general a very bad idea to take an observed population and try to reconstruct from it by inversely applying selection effects what the original population was. Because, of course, you may not have seen any low mass binary black holes, 4 + 4 solar masses, but you don't know whether it means there were none there or whether there were some there, but you have a selection effect against it. So what instead you do is you apply selection effects to your model, and then you say, OK, but does that match the observations? How probable is it that I would have gotten those observations given the model? You can never be 100% certain, but you can say, look, if my observations tell me that I should be detecting loads and loads and loads of 40 + 40 solar mass binaries, and LIGO hasn't seen a single one yet, there's something wrong with that model, right? If, on the other hand, I'm predicting that, well, roughly the mass spectrum of my predicted observations is, let's say, maybe scales roughly as the initial mass function, which is m⁻².5, right? And the selection effects, at least at low masses, are such that you actually have a selection effect that goes like m to the plus 2.5. Those cancel each other out, and you end up with a prediction for a roughly flat in mass distribution, and that's roughly what LIGO is seeing. OK, so maybe that model is not completely insane.
OK. I hope, of course, that you're wrong about the black hole spin magnitudes. But let's say that you're right. Then how are we going to tell the difference between the different formation scenarios, if not the spins?
So, OK, so there are a couple of things we can do. One is I think there could still be differences in mass distributions. I mean, your colleagues have argued, for instance, that you might, if you really have dynamical mergers, you might end up hierarchically forming more massive black holes that are going to be in the mass gap that would be due to parent stability supernova, right? So, OK, for people who haven't thought about this, right, you might expect, so Stan has argued for this, that you would have a gap between roughly 60 and roughly 130 solar masses, order of magnitude, where you don't have any black holes because their progenitors would explode in parent stability supernova. But if you merge together in a globular cluster a 40 plus 40 solar mass black hole, you form an 80 solar mass black hole. And if you keep the black hole in a globular cluster, it can merge with something else again. And in that case, OK, you end up saying, look, there is something that a merger companion that has 80 solar masses. OK, that's something about your channel. But I mean, another approach, by the way, Fred, is to say, look, I'm going to be agnostic. I will take an approach of saying, I don't know anything about the models. I will just look for clusters in my population where I cluster along all of the possible parameters, the masses, the spins, any other properties, the way that people have, let's say, approached gamma ray bursts and noticed there were short hard bursts and long soft bursts, and they were spatially distributed in different ways and so on. We can try doing that, and we've in fact written some papers describing some of the mechanisms you could do this specifically for gravitational wave events. With 7 events, it's too early to look for this kind of clustering, but we've argued that with already, let's say, 100 events, you could do this, and you might start seeing different clusters, and then you might associate them to different channels.
Vicky had a comment on this.
By the way, there are other measurables in connection to your question, is eventually merger rate as a function of redshift. That's something that I know you and I have talked about. It's something I'm working on in my group, and also Daniel is about to scoop me, I found out recently, but that's a different discussion. Okay, my question is, how do you reconcile your guess or educated guess that the black hole spins are small with the black hole spin measurements in high mass X-ray binaries? I have my own thoughts, but I'm curious to hear yours.
OK, so first of all, maybe just a very quick statement of why I actually think black hole spins are small, particularly in this channel, right? And the very simple argument is, of course, it's very easy to have a tremendous amount of spin in a star. If I take a giant star and I spin it at a small fraction of breakup, it has such a large moment of inertia, it has this chi parameter, this dimensional spin parameter corresponding to angular momentum divided by mass squared of 10,000. Not a problem. Problem is, if I ask how much of that angular momentum is in the core and how much is in the envelope, it's all in the envelope. So by the time I strip away the envelope, I end up with a core that has a spin parameter of 10 to the minus 3, unless I have a huge amount of differential rotation. So if I have a huge amount of differential rotation, I can get around that. Now, of course, I can still get around it in other ways. For example, if I manage to tidally log the 2 stars after removing the envelope and so on, but it becomes very tricky. So indeed, the question is, what about the high mass X-ray binaries? So simplest answer is, I'm skeptical about the spin measurements in the high mass X-ray binaries, and I know Ramesh is going to hate me for that.
She's standing next to you.
Don't run out of time.
Thank you. Perfect. Secondly, I think they go through a different channel. And I think I know which channel they go through, but we can talk about that later.
Don't you dare scoop me there.
No comment. Thank you.
Okay, I think we need to move on. Let's thank Ilya again.